Okay, so it has started recording. Yeah, so fine. So we are basically starting from these probabilistic graphical models and evidence lower bounds. And there's this one concept that we need to know if, to understand all this thing, that is of scale divergence. So okay, so what is the scale divergence? So basically, if you have two random variables x, y, right? They have their respective distributions, right? Px, Py. Scale divergence is a measure is uh okay, very hand in the very hand wavy fashion I'm saying this, but scale divergence is a measure of how dissimilar or similar these two distributions P and Q are. Okay. So this outer thing, this is basically the notation for expectation, right? And so the expectation is under P of X. That is something that we need to keep in mind. And this expectation is of log Px by Qx, right? So, I mean, to start with, to understand this thing in a very simple way, perhaps a good example would be, let's say that X and Y, these two are, let's say, discrete random variables, right? Discrete random variables, meaning that assume they lie on a countable set, basically, okay? So that's uh, let's say that is what so these two are basically discrete random variables. So basically you can basically define the distribution of x and distribution of y uh, by specifying what is the probability that the random variables can take at upper discrete points, right? So basically you can define the distribution in a point-wise manner, that's all. So let's say that so in that case, what will this definition boil down to? So DKL between P and Q, right? This will become what? So we have an expectation. So again, let me write down the definition first. So this is expectation of log P of X by Q of X, right? Now for discrete random variables, since the distribution is basically discrete, this expectation can be simply written as follows, right? So you have summation with X. So the expectation will become a summation because these are discrete random variables. Otherwise, it would have been integral, right? So this is X belonging to some support of X, right? This is X. So this calligraphic X is basically the support of X, P of X log P of X by Q of X. Okay. So for discrete random variables, this is how it will look. However, in general, this thing will simply be DKL between P and Q, which will be equal to integral P of X log P of X over Q of X dx. And the integral is over the support of X, so X belonging to calligraphic X. So, I mean, if you look at it the first time, this might look very, I mean, for the lack of better word, unnatural, right? I mean, why should this thing become, why should this thing be of interest at all, right? I mean, there is a log of P of X by Q of X, and there is an expectation outside. This doesn't look very straightforward. Uh, but so we will try to make sense of this thing by noting down some observations, okay? Uh, so let's see what this is, okay? Uh, so maybe need to add one page. Okay. Let me just add some pages before. Cool. Right. So here it is, right? So this is your So let's note down some observations, right? So some observations. Observations. So first observation is that uh, so this TKL. So basically we are going to justify that the scale divergence is some sort of distance between two distributions P and Q. Okay. I mean, I'm using this word distance here, but it's not exactly a distance, but just for the sake of intuition and just for the sake of understanding, you can think of it as distance. But it's not a distance. I mean, it's full disclosure. For the sake of intuition, you can think that, okay, the scale divergence between two distributions is like distance between two distributions, but strictly speaking, it is not a distribution. Okay. So we'll see why I'm saying these things, but that is the bigger picture. So just let's keep the bigger picture in our head, and we will slowly, boil things down into easier pieces and sort of make sense of everything. So the first claim or first observation is this that the scale divergence between P and Q, this is always a non-negative quantity. So it will be zero or greater than zero. Okay. How is that? How can we see that? Well, it's so let's try to see why this is true. Okay, so let's look at this thing minus DKL and P and Q. Okay, so this thing from definition, right? So this is the definition of KL divergence, right? So this is what minus expected value of P of X log P of X over Q of X. So this is by just by definition, right? Uh, so what, so you can take this negative sign inside, right? Inside of the expectation because this expectation is basically a linear operator, right? So you can take this negative sign inside and this thing will become expectation under P of X, okay? Log. So negative log Px by Qx is nothing but log Qx by Px, right? So this will be just log Qx by Px, okay? Now we are going to apply some inequality here. Okay, so let us look at it. So that thing was minus. So minus DKL between P and Q is nothing but expectation under P of X log U of X over P of X, right? This is what we just saw. Now what we are going to see, what we are going to use is something called Jensen's inequality. Okay. So I'll just write it down what is Jensen's inequality here. So let's say that you have a uh, let's say that you have a function like this, right? So this is, I mean, this is your y-axis, okay? This is your y-axis, uh, and maybe this is your x-axis, and this is your function, right? So this is your function f. Okay. Now let's say 2 points, A and B, right? So remember that this is a concave function, right? Concave function is which uh like the curves I mean this is I mean I don't know how do you visualize it, but con I visualize it as concave functions are those where it's like the curve is facing upwards basically, okay? So if you have a function like this, consider 2 points, right? So let us consider this point here, A, and consider this point here, let's say B, okay? And you have correspondingly, you have f of A, and similarly, you have f of t, okay? Now, consider let us consider a middle point here, okay? Which is A plus B by 2. So the point which is exactly in the middle of A and B, So this point is a plus b by 2, okay? Now let us connect, basically let us just connect these 2 points on the curve, okay? Uh, right, so um, I'm just right. So what is the value of f f of a plus b by 2 basically, okay? So the value of f of a plus b by 2, that value will be something which will lie here, right? I mean on the curve, okay? And next, just uh, look at f of a plus f of b by 2, okay? So f of a plus f of b by 2 will be something which will lie on this line here, somewhere here. In fact, it will be exactly here, below this point. This is simply by just, I mean, you can actually do some geometry here and show that this value is this this thing which is f of a plus b by 2. This value will always lie above this point which connects the 2 points here, and hence the inequalities look something like this, that f of a plus b by 2 is always greater than equal to f of a plus f of b by 2. And in general, for any convex function, if f is a convex function, instead of taking a plus b by 2, you can in general, so a plus b by 2 is basically average of a and b, right? And in general, any average, so any, placeholder or a equivalent interpretation of average is expectation, right? So in general, any average, for any average or any random variable x, f of expected value of x will always be greater than or equal to, so and to expected value of f of x. So I mean, if you want to look at it, so you can think that this is the average value of x, okay? And this entire thing is average value of f of x. So f of average is greater than average of f is what is how you can remember or sort of think about it. And this is exactly, this is something which is called, this is a, okay, yeah, so this is what is called as Jensen's inequality. This is what we call as Jensen's inequality. So we are going to use, so why I did all this thing, because we want to use this inequality. Why? Because I mean, if you look at it here, see, you have expected value of log of some qx by px, right? Uh, Looks like, right? This, the graph for log function is something like this, right? It looks something like this, which is a concave function. So we can, so since the Jensen's inequality applies on concave functions, we are going to apply it here in our context, right? So remember the way we remembered it, right? So expected, so look at RHS. The RHS of Jensen's inequality tells us that expected value of f of x. So now here we have an expected value and this is our f of x. This thing is basically less than or equal to, I'm using this sign, this inequality, but I'm looking at it from here, right? So this is less than equal to expected value of f of x is less than or equal to f of expected value of x. So what is f? F is our log function. And what is expected value of x here? So you have an expected value of p of x. And what is x? For x, for us, the random variable now here is q of x by p of x, right? So that thing will become expected value of p of x, qx by px. Uh, Let me know if this step is clear, or if it's not clear, let me know. Uh,
Well, it's clear, but the only thing is that I mean, do we need to show that the given function is a concave function? I mean,
yeah,
that
yeah,
itself
we
would
need to.
require some time. Okay, okay,
Yes, yes, it's required because otherwise we won't be able to apply Jensen's inequality,
okay.
right?
So what is the
So
what is the analogous of the Jensen's inequality for the convex function?
the signs will reverse.
Okay,
So for convex functions, f of expected value of x is less than or equal to expected value of f of x. So I mean, if you want to think about it in the other way, just replace. So if f of x is concave, neg minus f of x will be convex, right? I mean, if a curve is facing like this and you take the negative of it, it will start facing down, right? So it will become convex now. And so all you have to do to derive the result for a convex function is multiply this equation or inequality with a negative sign, and you will get the corresponding result for convex function, right?
yes, yes,
Right. So we have this result now. Okay. So what can we say about this thing? So this thing is equal to log of. So so what is expected value of q of x by p of x under p of x, right? So let us. So I will just write this down for discrete random variable, but it is true for continuous random variables as well. So expected value can be written as how? This can be written as summation x belonging to some calligraphic x, right? Then we have p of x because this that is what this expectation is under, and then the value of the random variable, which is q of x by p of x. This is just by definition of expectation, right? And now here we can see that p of x and p of x will, sorry, p of x and p of x will cancel out basically, right? And all we are left with is, so this is just log of summation of x belonging to capital X, q of x. Now we know that q of x is a distribution over x, right? So in that case, when if you are the by the property of distribution, we have that the summation of q of x over all x is nothing but 1 because q of x is a distribution, right? So this thing will simply become log of 1. And we know that log of 1 is nothing but 0, right? Hence, we just saw that minus dkl between p and q, this thing is less than, remember this was less than, right? So less than or equal to 0, right? In other way, what we can say is that dkl between p and q is greater than or equal to 0. So, so this is what we tried to prove, right? So so we have proved that. Okay. So this is one property, right? This is one important property that uh, DKL is a non-negative quantity. So it can never be negative. And if you remember what I told at the starting, right, that you can think of KL divergence as distance between two distribution. Remember, recall that distance can also never be negative, right? Like distance between 2 points always has to be a non-negative quantity. Either it is greater than 0 or it is 0, right? So we see that property coming here. Like uh, through these properties or observations, we are trying to sort of relate how KL divergence is similar to distance, similar to the concept of distance. Okay, so this was first observation. Let us look at another observation, right? So here is another observation that if okay, so if P is equal to Q, right? Then DAL between P and Q this thing is equal to 0. So this again, this is very similar to the property of distance, right? Or metric, that when is the distance between 2 points 0? If you recall, the distance between 2 points is 0 only when both the points are same, right? So this is exactly like that. So that KL divergence between two distributions is 0 if uh, P is I mean, okay. So there is some technicality here. So I am saying that if P is equal to Q, then KL divergence is 0. I am not showing here that if KL divergence is 0, then P is equal to Q. So uh, so I mean, what I want to say is that uh, okay. So what I want to say is that I am here. What I am showing is that if this is true, this implies that DKL between P and Q is 0, right? I'm not showing the other way around. This statement right now is just one-sided. I am showing that P is equal to Q implies that KL divergence is 0. Okay. Uh, so let's show this thing. So it's quite simple. So what was the definition of, again, we just have to go to the definition of KL divergence, right? So this is again expected value under P of X log P of X over Q of X, right? Now, if P is equal to Q, this thing is nothing but P of X log P of X over P of X, right? Because P is equal to Q. And hence this thing cancels out. And hence this thing is nothing but 1, right? And log of 1 is nothing but 0. And hence this thing is 0, right? Expected value of 0 is 0. That's all. So, so basically you can see that if P is equal to Q, then KL divergence is quite simply it's 0. Okay. Uh, what I am not showing here is that, I mean, there is another observation which I will just write down, uh, but I'm not going to prove it that if DKL between P and Q is 0, then P is equal to Q. So this is the other, so as I said, right, that I'm not showing this part of the property, but this is exactly the statement for that, right? So this statement is basically saying that DKL between PQ is equal to 0 implies that P is equal to Q. In the previous observation, we saw the other, we proved the other way around, right? That if P is equal to Q, then KL divergence is 0. This is like the opposite of it. But this is nonetheless, this is true. I'm not going to prove it because proving this will actually require uh, some mathematics that is unnecessarily complicated for our purposes, right? So we'll just skip that part and we'll just sort of state this and just just take it for what it is. Right. So these are the properties of scale divergence. Okay. So if I have to draw a comparison of scale divergence with a distance metric, right? So let us see that. So if you have, let's look at it. So scale divergence, we have on one hand we have scale divergence, and on the other hand we have, let's say, distance metric, right? So what are the properties of distance metric? They're quite simple, right? So one property of distance metric is that if D is the distance metric, right? So D of x comma y is always greater than or equal to 0. That, as I said, that distance is a non-negative quantity, right? Another property of distance metric is that D of x comma y is equal to 0. This implies, and if and only if, like if x is equal to y, right? Okay. Third property of distance metric is that d of x comma y is equal to, this is symmetric property, d of y comma x. So distance between x and y is equal to distance between y and x, right? That is another property of your distance metric. And there is another property which is quite essential, which is called the triangle inequality, which basically tells us that d of x comma y is always less than or equal to d of x comma z plus d of z comma y. This is something called triangle inequality. So, I mean, these are the properties that needs to be satisfied by any function d in order for it to be called a distance metric, right? Now, what do we have for KL divergence, right? So, the one property of KL divergence that we saw was, well, dKL between P and Q. This is also a non-negative quantity, which is similar to distance metric, right? Second property that we saw was that, well, if dKL between P and Q is 0, this implies, like, if and only this is if and only if P is equal to Q. Okay. Now, what are the properties that we didn't see? I mean, which are basically not true, is that pKl between P and Q. So this thing, so the symmetric property basically, which holds for distance metric, is not true for KL divergence in general, right? I mean, basically you can just write those things down, because the ratios p of x by q of x will change to q of x by p of x, and log function does change with the order, right? So the KL divergence is not symmetric. That's one thing which is different from distance metric. And the fourth property that we saw, which is true in distance metric, so that is the triangle inequality, also doesn't hold for between P and Q is not less than or equal to dKl between P and R plus dKl between R and Q. So this also doesn't hold. Okay. So, I mean, so basically what we want to say is that this property checks out. Okay. The second property also checks out. No problem. However, these properties doesn't check out, right? Third property, which is that of symmetricity, doesn't check out, and fourth property, which is the triangle inequality, also doesn't check out. So that is why initially I was saying that, you can think of KL divergence as distance between two distributions. However, it is not a distance. That is why we call it a divergence. We call it KL divergence and not KL distance. That is there is a reason why we call it this, why we come up with this, term divergence and not a distance, right? Uh, let me see it later. So I mean, hopefully I have convinced you that you can, for the purpose of intuition, you can think of KL divergence as closeness between two distributions. Or if you want to, be a little bit hand wavy, you can think of it as distance between two distributions. However, strictly speaking, it's not distance. Okay. So I mean, if someone goes and comes and asks you, oh well, is this a distance? No, it's not a distance. It is just a measure of closeness between two distributions. For the sake of intuition, we can think about it as a, distance, but we should never call it a distance. Okay. So that's,
I have a
yeah,
question here. So,
yeah.
like, I mean, what is the rationale behind taking this term log of px by qx? Because in the
Right.
entropy measures, we could have either taken simple px, or in the cross entropy measures, we could have taken simple qx. But then, what's the rationale behind taking this log of px by qx? And moreover, we are not
Mhm.
using any negative symbol here.
What do you mean by negative symbol?
I mean, if you could have, I mean, just to follow the, I mean, the notion of, I mean, the popular equation of the inequality of the, I mean, popular equation of the entropy, say, minus
Mm-hmm.
px, and then say log of
Mm-hmm.
px, summation of that kind of thing. So
Right.
it's okay. I mean, I do not pay much, I mean, emphasis over the negative sign, but then the rationale behind this term log of px by qx,
Mm-hmm.
uh,
Mm-hmm.
uh, uh, yeah, I'm thinking about it. Yeah.
Okay. So these all of these things are actually connected. Okay. I mean, this actually comes from information theory, but if I have to give you some intuition, you can write this thing as expected value of p of x log p of x uh, minus expected value of p of x uh, log q of x, right? So this thing actually does so Kale divergence does contain a entropy term, which is the first term. So this is h of p, right? So this is entropy of p. The first term is entropy of p, uh,
Yes.
right? And the second term is actually plus. So this thing is actually your cross entropy term, right? So this is
Yeah.
like cross entropy of between p and q. So you can see here, right, that KL divergence is actually difference between cross entropy and your true entropy. So another way to think about it. So I mean, from this, I'm going to say this from a information theory perspective. You have a random variable x, right? Do you know that the entropy is the amount of bits that you require to uh, basically code uh, the least amount of bits that you require to uh, write down express the random variable is your entropy h of p, right?
Every
Do you know
every
that it
every every number of
yeah,
the bits required.
yes, so the least amount of average bits that you require to express a random variable x is h of p. And you can think about cross entropy as, let's say that the actual distribution of the random variable is p of x. However, to express that random variable, you are using some another distribution which is q of x. So you can think about cross entropy as the average amount of bit that you require to express a random variable x in terms of q of x. Okay. So
Yes.
the difference between two is basically what is the extra amount of bits that you are using. So what is the overhead basically that you are using to express the random variable x, which follows the distribution p of x, but you are trying to use another distribution q of x to uh, express it. So I mean, from an information theory perspective, that is how you can think about it. So uh, does that make sense?
Yes, yes, very much. Yeah, now I understood. Yeah. So this scale divergence represents I mean, gives the value of the extra number of the bits required to
Yeah,
encode
on an average, what
the
is the extra
yes,
number of bits that you require to express the random variable whose true distribution is p of x, but you are using an incorrect distribution q of x to express it. Yeah,
right, right. Yes, correct. Yeah, fine. Thanks.
right. So that is information theoretic perspective. But I mean, to talk about these things, entropy, these things will take us on a something which is not of which will act as digression. So I didn't want to go there. But yeah, I mean, that's another view of scale divergence that you can think about this in terms of coding theory. That's a great way to actually understand scale divergence if you want to really understand it from first principles, right? So that's scale divergence, right? Let's add some more pages now. Okay, so now let's get started with our real stuff that we wanted to talk about, right? Um, okay, that I think it's 15 minutes. So what I will do is I will just stop the recording and make this like this thing as a preliminary or something, okay? Uh, is that fine? I will stop the lecture and cut this as a new lecture, which is just preliminaries. And then we will start with probabilistic graphical models, and we'll call that lecture one. So I'll just do that, right? So I'm going to stop recording.